So we've been looking at these kinds of differential equations, x prime equals a x, where x of t is a batch of unknown functions, but let's say it's just two unknown functions, x of t, y of t. And capital A is a 2 by 2 matrix of constants. So these are linear homogeneous systems of differential equations with constant coefficients. And they are autonomous differential equations, so that means in the phase plane, they specify at each point a particular direction in which trajectories are going to travel if they pass through that point. A direction and a magnitude, so it's actually velocity vectors of trajectories that are being specified at every point. And you can see that if you put in x equals 0, vector x equals 0, so if you focus on the origin, then you get for your velocity vector 0, right? You get x prime equals a times 0, which is 0. So while everywhere else you might have arrows pointing in different directions, at the origin you actually have the 0 arrow, which says don't go anywhere. And that's why x of t equals 0, 0 is just a constant solution, is an equilibrium solution, anytime you've got one of these differential equations. Now, we've seen a pretty nice way of writing down a general solution to any one of these. So given any one of these differential equations, you can solve the eigenvalue problem for the matrix A and then come up with a general solution and figure out what the trajectories look like. But the pictures are very different, right? Like sometimes you can get spirals, spiraling in or spiraling out. Sometimes you get, just circular or elliptical orbits around 0, 0. Sometimes you get, some eigenvector directions that separate the plane into different regions, and between those regions you get some kind of curved solution trajectories that look a certain way. So there are all kinds of different things you can get. And what I want to do is summarize, so nothing particularly new, but I want to summarize in kind of an organized way what are the different things that you can get. And hopefully we can come up with a way to know which of the different pictures we're looking at without going all the way down to the general solution. So let's just start by trying to organize things a little bit. So let's see, you start by solving the eigenvalue problem for A, right? So you get some eigenvalues like lambda 1, lambda 2, and some eigenvectors like v1, v2. And yeah, okay, maybe lambda 1 equals lambda 2. Maybe you don't have enough eigenvectors. There are things that can go wrong, but let me just set up this notation and then think about the possibilities. So the first thing to think about, I guess, is whether the lambdas are real or complex. So we're definitely going to get at least one lambda. The reason for that is that lambda is the root of a quadratic polynomial. It's the root of the characteristic polynomial for A. So we will get at least one lambda, and since it's a root of a quadratic polynomial, for a quadratic polynomial, there are basically three cases. You either have real distinct roots, or you have repeated roots, or you have complex roots. So let's start by splitting things up like that. Okay, so here's our first sort of split. So maybe we'll make this a tree where we start by finding, solving the eigenvalue problem for A, and then there are three possibilities. We either end up with two real distinct lambdas, lambda 1 not equal to lambda 2, and they're real, or they're complex, but since A is a matrix that just has real coefficients in it, we have seen that you will get a complex conjugate pair of roots in this situation. So we can write them as alpha plus I beta, and the other one will have to be alpha minus I beta then. Or there's the repeated roots case, which we actually have not really talked about. But I mainly want to focus on these two, although I'll fill out the tree a bit. So we can already say something about these cases. In this case, we know that we end up either with a stable or unstable spiral centered at the origin, or we end up with a stable center. And in this case, we end up with some kind of node, like a stable node or an unstable node, or we end up with a saddle point. But let's say a little bit more. I think the complex case is probably more fresh in your mind since that was a previous lecture, so let's do that one first. I would say the main thing to focus on is alpha here. So you can have alpha greater than 0, or alpha equals 0, or alpha less than 0. Now, if alpha equals 0, that's a stable center. And you saw that on one of your homework problems. So that's where lambda is just plus minus I beta. Lambda is purely imaginary, right? Then your solution has the form e to the, a complex solution is e to the I beta, right? Times just pick one of your eigenvectors, v. That would be a complex solution. So when you write this out in terms of real and imaginary parts, you've got a cosine beta, t. You've got a cosine beta t and a sine beta t sitting there, and no overall exponential sitting out in front. And we've seen how this is going to give us circles or ellipses for trajectories. So maybe we'll make a little picture for each one. You get something like that. This is the phase plane, so this is like the xy plane there. All right, when alpha is greater than 0, you end up with this overall factor of e to the alpha t multiplied by what I was just describing, this e to the I beta t times whatever eigenvector you chose to go with, alpha plus I beta. So it's the same thing, but with an overall e to the alpha t, this time with alpha not being 0. So, well, if alpha is greater than 0, then this is exponential growth sitting out in front. And if alpha is less than 0, then what you've got is exponential decay sitting out in front. So exponential growth, this would be an unstable spiral. And exponential decay here gives us a stable spiral. With the words stable and unstable referring to sort of the stability properties of 0, 0, of the origin. Are things near 0, 0 exploding away from it or going towards it? Here they explode away. So basically a picture like this, but also scaling things out as time goes on. And, I don't know that they will go sort of clockwise like this. They could go the other way. So this picture is just showing one example. You could also have a stable spiral, exponential decay, basically this picture, but things are coming in. And I'm just showing two trajectories, but the plane is filled with these different trajectories. And I'm showing them kind of hitting the origin, but they really just spiral forever. It's just that you have to zoom in very close to see the smaller spirals, since exponential decay and exponential growth are very, very quick. So if I want to make this picture qualitatively better, then I should zoom in here, maybe erase these parts, and then show the finer things that are going on. And if you zoom in further, you'll see that there are tighter and tighter spirals there. So they never actually reach the origin. All right, so you can see that you don't have to go all the way down to the general solution to know which general picture you're in. Maybe to draw a more exact picture, you will need the general solution, but if you just want to know, like, is this an unstable spiral or a stable spiral? Well, then it's enough to just look at the real part of the eigenvalue. Let's see if we can come up with a similar sort of classification of the different possibilities in this case, where you have real distinct eigenvalues. So as before, your solutions are going to be like e to the lambda 1 or lambda 2 t times an eigenvector, right? E to lambda 1 t v1, e to lambda 2 t v2, these are what your solutions look like. And okay, maybe I should put the numbers, because your general solution looks like c1 plus c2 e to the lambda 2t v2, like that, right? And then if lambda 1 and lambda 2 are both positive, then you've got what we have seen, that you get an unstable node. If lambda 1 and lambda 2 are both negative, we've seen that you get a stable node. And if they have different signs, one positive and one negative, then we've seen that you get a saddle point. So that was the thing we drew out in detail 2 lectures ago. So we can split it up, maybe something like this. I think this is a little bit hard to read. Maybe I'll just call this the negative case, the negative positive case, and the positive case. Probably easier to read that way. And can make a picture for each one. So in each case, you've got these eigenvectors. If you want to draw an accurate picture, then you need to know about the eigenvectors. Just like over here, I wasn't actually drawing accurate pictures. I'm just giving the general idea. I don't know that the spiraling out here will be clockwise. You need to actually look at the solution to know which way it goes. You'll have to know what the eigenvectors are. Similarly here, there are some eigenvectors, so I'm just going to draw some, how about in blue, some random vectors. Like maybe these are our eigenvectors. And actually, let me draw the lines along the eigenvectors instead. In each case, you have these. Let me just copy the same image. All right, so these are the lines along the eigenvectors, and they are actually they are two very special solution trajectories are being shown here, or 4 very special solution trajectories are being shown. They're the eigensolutions, so the ones that actually look like e to the lambda 1 or lambda 2 t times an eigenvector, rather than being a linear combination of 2 of those. So these show you the eigensolutions, but I should put some arrows to indicate which way they actually go. As you run time towards the future, in this case, you've got exponential decay sitting in front as a scalar multiple out in front, right? So this is like the future direction there. And then here, this would be the future direction. When both are positive, you have exponential growth. So we can give these their names. This one is a stable node, unstable node, and of course, I should show more solutions than just the extra special ones. What do most solutions actually look like? They are the curved looking trajectories in between. So to actually show which way the curve goes, you need to know which of the 2 eigenvalues is bigger. We've seen that. But let's just pretend that it goes one way or another and draw some solutions. I'm realizing that there's no sense in having the coordinate axes, the x and y axes, actually in these pictures, since the eigensolutions themselves make for better axes for these pictures. So I'm just going to get rid of clutter, I'll delete these axes. So something like this. And that's just an example. So you'd have to look at the actual eigenvectors if you want to know which way these blue lines go. And you would have to look at the actual, you'd have to compare the eigenvalues, which they're both negative, but which one is more negative to figure out how these are curved exactly. But you see the stability that all trajectories are coming in. And you get basically the same picture for this one, but with the arrows pointing the other way. And then for the middle one, that one is called a saddle point. And now your eigensolutions look pretty different, right? There's one that looks like e to the negative number, lambda 1, times t times an eigenvector. And there's one that looks like e to a positive number times t times the other eigenvector. So as time goes towards the future, whichever one is the eigenvector that goes with the negative eigenvalue has solutions decaying towards the origin, and whichever is the eigenvector that is associated with a positive eigenvalue has solutions running away from the origin in a straight line. And those are the two special solutions, but in between you've got some curvy looking ones. And you know, most solutions will look like these. If you just pick a random solution, it's probably going to be one of these curvy looking ones. And I'm actually just going to not say anything about this case because, well, we haven't studied a way for writing down the general solution in this case. And as far as the picture goes, I'm actually going to show you something later in this lecture that gives you an idea of what happens. And if you want to learn more about how to write the general solution in this case, then there's a section about that in our chapter that you can read, but I'm not making it an official part of the course. So whatever the picture is that goes with this situation is going to be actually something interesting that is somewhere between a node and a spiral somehow. So we'll see that later. Okay, so this is our sort of taxonomy of the possible phase portraits types, possible stability properties, and possible characters of solutions around 0, 0 for this kind of differential equation. So you can read this kind of like a flowchart, I guess. Start from here, solve the eigenvalue problem for A, and then ask yourself, are the eigenvalues real or are they complex? If they're real, follow this branch, and if they're complex, follow that branch. And then ask yourself various other questions. Are they both negative? Are they, or if they were complex, is the real part positive, etc. And as you answer the different questions in the flowchart, you end up in different situations. But what I'd like to do in the next video is improve the flowchart a little bit and not require you necessarily to solve the full eigenvalue problem to decide where to go down the flowchart. So we'll look at a certain very cool shortcut in the next video.